All right, everyone. So welcome back to week 3. So we start the second third of the course, and what we're going to do is we're going to pick up where we left off really last Tuesday, and we're going to start talking more about derivatives, and particularly we're going to introduce some rules for derivatives. So we'd previously done rules for limits, now we'll do some rules for derivatives. Okay, so the first place that we can start is some rules that we've already seen, and one thing you might notice is that there's this d by dx that I have sitting around. And the reason for that is that there are really two notations for derivatives. So we've so far been using this notion with an apostrophe, so f prime of x. That notation comes from Isaac Newton, who was one of the uh, inventors, discoverers, creators of calculus. And then there's this d by dx notation, which is it's describing the same thing. You could think about it as it's saying the derivative with respect to x of whatever comes afterwards. And that notation comes from the German mathematician, what is his name? Wilhelm? Whatever, Leibniz, um, who, depending upon whom you ask, was either a plagiarizer of calculus or an independent co-creator of calculus. So they mean the same thing. Um, you can use whichever one you want. For the most part, I stick with the prime notation, but other times I kind of mix the notations around a bit. So just for clarity, whenever you see a d by dx, it just means a derivative with respect to x. Okay, so some of the rules that we've seen so far. So if you take the derivative of any constant, you get 0. I'm going to skip over the second rule for the moment and then come back to it. The third rule is that if you take the derivative of a constant times some function, that's the same thing as saying the constant times the derivative of that function. Um, we would expect maybe that to be the case given what we know about limits and how we could pull constant multiples out in front of limits. And then in the same way that we could switch the order of taking a limit with addition or subtraction, we can do the same thing with derivatives. So we can switch the order of taking a derivative with adding or subtracting. Now the second rule tells us something very particular about powers of x. So if you have x to the n, where n is some integer, we'll start with positive integers for now. If you want to find the derivative of x to the n, that is going to be n times x to the n minus 1. So in other words, what you do to find the derivative of x to the n is you pull the exponent out in front, so you multiply the exponent out in front, and then subtract 1 from the power. So this one is maybe a little bit surprising because we didn't have any real rules for something like this um, for limits. So this is something very different from limits. So where does this come from? Well, let's start off with our standard limit definition for a derivative. So we'll take the limit as h goes to 0 of f of x plus h minus f of x, where f of x is going to be x to the n. When we do that, we get the limit as h goes to 0 of the expression x plus h all raised to the n minus x to the n, and then it's all divided by that h. Okay, now x plus h to the n. That is saying we're going to multiply the quantity x plus h times x plus h times x plus h n times. And when we expand that out, what we would get is an x to the n times an n x to the n minus 1 times h plus some polynomial times h squared. We're not overly concerned about what that polynomial is, just it's got every term in that polynomial is going to have at least h squared. So some will have h squared, others will have h cubed, and so on. Now what we can do is say, well, we have an x to the n, and then we have we're going to also have to subtract off an x to the n. And that's good because that gets rid of all the terms that have no h in them. So every term in the numerator now has an h in it. So what we can do is factor out an h from our numerator, which will give us h times um, n x to the n minus 1 plus h times this polynomial containing all the other stuff. We'll then cancel the h that we factored out in the numerator with the h in the denominator, and our problem now reduces down to finding the limit as n goes to 0 of nx to the n minus 1 plus h times this other polynomial, but as h goes to 0, that second term goes away, it goes to 0. And that just leaves us with nx to the n minus 1. So that's where this rule for powers of x comes in, and we're going to use it pretty frequently. Okay, so something else that we could look at are what are called exponential functions. So say, for example, we wanted to find the slope of the tangent line 2 to the x at a equals 0, and also 3 to the x at a equals 0. Now, so far, we haven't devised any rules for dealing with exponentials, so things where we have a number raised to the power of x. And that's okay because we're not really finding it, we're just going to use this as an example to get to something else. Right, so pictorially what we have here, the red line is the function 3 to the x, the blue line is the function 2 to the x, the orange line is the tangent line to the red line at 0. The green line is the tangent line to the blue line at 0. And then there's this black line. And the black line is just a line that's going through the point 1 that has a slope of 1. And the reason for that, why I have this line with slope 1 in there, is that we see that as h gets closer and closer to 0, the quotient that we would have for, so the slope for the line 2 to the x as x goes, or at x equals 0, is sitting at about 0.69, and the slope for the tangent line for 3 to the x at 0 is a bit over 1, so it's about 1.1. And what would be really interesting is to find the number that has the property that this number, when raised to the power of x, the slope of the tangent line at 0 is 1. So what we'll do is we'll define a number that has this property. We will define this number e, which is the first few numbers in the decimal expansion. It's 2.718281828, and we'll just define e to have the property that the limit as h goes to 0 of e to the h minus 1 all over h is 1. Okay, so let's go and find the slope of the tangent line to a polynomial and then also something else involving e. Okay, so first we'll take the function 4/5 x to the 4 minus 3x cubed plus 2x minus 7, and we'll go find the derivative of that. So again, what you can see is I'm kind of mixing this Newton and Leibniz notation just for simplicity. So the first thing that we can do is we can go and pull out our sum rule, which says that instead of finding the derivative of the whole thing, we can find the derivative of each term, and then add or subtract those as appropriate. So instead of the derivative of just f of x, we'll have the derivative of 4/5 x to the 4 minus derivative of 3x cubed, and so on. The next thing that we can do is we can pull out constant multiples. So we'll get 4/5 times the derivative of x to the 4 minus 3 times the derivative of x cubed, and so on. Now what we've done is we've reduced our problem down to finding the derivative of powers of x, or constants in the case of the last term, which is quite nice. So, from our power rule, the derivative of x to the 4 is going to be 4x cubed. So again, take the power 4, multiply it out in front, and subtract 1 from the power. The derivative of x cubed is 3x squared, the derivative of x squared is 2x, and so on. So we just wind up with 4/5 times 4x cubed minus 3 times 3x squared plus 2x for our derivative. And then just multiplying a couple of constants back together, we get 16/5 x cubed minus 9x squared plus 2x. Okay, and we said we want to find the tangent line at a equals 2 for this function. So we need to first find f of 2, which is easily found to be minus 71/5. We can then find f prime of 2, which is minus 32 fifths. And that tells us from putting everything into our tangent line equation, the tangent line to f at a equals 2 is going to be minus 32 fifths x minus 7 fifths. So next, we'll use the same kind of techniques to go and find the derivative for 3 halves x squared minus 7e to the x. So the first thing that we want to do is we want to pull out our sum and or difference rule to go and split up our function into finding the derivative of 3 halves x squared minus the derivative of 7e to the x. Then we can use our constant multiple rule to go and pull the constant multiples out in front. And then in the first term, we'll use the power rule to get a derivative of 3x, but we still need to deal with the derivative of the e to the x part, because so far we don't have a derivative for that. So the only thing we can do with the derivative e to the x is use our limit definition. So we'll take the limit as h goes to 0 of e to the x plus h minus e to the x all divided by h. When you have a base raised to a number or something plus something else, so in this case we have e to the x plus h power, you can split it apart as e to the x times e to the h. They're the same thing. Just as a very quick example of this, suppose we had 2 to the 5. 2 to the 5 is 32. We could write 5 as 2 plus 3, so we'd have 2 to the power of 2 plus 3. And I'm saying we could split that part as 2 to the power of 2 times 2 to the power of 3. 2 to the 2 is 4, 2 to the 3 is 8, 4 times 8 is 32 as desired. Okay, so now what we have is we have an e to the x that is common to both terms in the numerator. So let's go and factor it out of the two terms in the numerator. The next thing that we can say is because our limit is involving only h, e to the x is effectively a constant with respect to h. As h changes, e to the x does not change. So we can actually use our constant multiple rule for limits to pull the e to the x out in front of the limit. So then we're left with e to the x times the limit as h goes to 0 of e to the h minus 1 all over h. And remember that we defined e to be the number that has the property that this limit is 1. So it turns out that the derivative of e to the x is itself e to the x. So e is its own derivative, which is kind of a cool property. Okay, so then using that, we just wind up with a final derivative of 3x minus 7e to the x. And now we want to go and find the equation for the tangent line. So we'll go and do the same thing. We'll first find f of 1. In this case, we're going to get 3 halves minus 7e. If you really wanted, you could go and do things as decimals, but my advice when going and working homework and tests and things is as much as you can, leave things as fractions or symbols until maybe the very end. The reason for that is if you start pulling decimals around early on, you're probably going to round things to maybe 1, 2, maybe 3 decimal places. And as you keep doing more arithmetic operations with the decimals, you're going to introduce round-off error, which really is what we found back on the first or second day with limits. So here, just leave things as symbols until maybe the very end. We know what f prime is. It's 3x minus 7e to the x. F prime at 1 is 3 minus 7e. So then we'll go and stick all of this into our tangent line equation. So f prime of 1 times x minus 1 plus f of 1. And that gives us 3 minus 7e times x minus 3 halves for the tangent line. Okay, we could also talk about higher order derivatives. So we found a first derivative, and we could find second and higher order derivatives, and they're quite straightforward. The second derivative is just the derivative of the first derivative. So we can see an example of that with this polynomial. So 4.9t squared minus 3t plus 10. So first we need to find the first derivative. So we'll go and use our sum rule, and then we would use our constant multiple rule and power rules as we've just done. We would get our first derivative is 9.8t minus 3. And then to find the second derivative, we just take the derivative of that, and we do the same kind of thing. We use our sum and difference rule, we use our constant multiple rule, then we use our power rule. And we wind up with 9.8 in the end. Right, so finding the second derivative, fairly straightforward. So now we can talk about how we would go about trying to find the derivatives for products and quotients. And these two are kind of unexpected. So remember that with limits, we said that the limit of f times g is just the limit of f times the limit of g, assuming that both exist. And for quotients, assuming that they both exist and the denominator is non-zero, the limit of f divided by g is just the limit of f divided by the limit of g, and neither of those is the case for derivatives. We get something quite different. Okay, so if we want to find the derivative of f plus g, so far the only thing we can do is use our limit definition for a derivative, so we'll go and do that. So we'll start off by finding the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x, and it's all divided by h. And now what I'm going to do is I'm going to cleverly add and subtract a quantity that it's probably not obvious at all why I'm inserting. So I'm going to add and subtract the quantity minus f of, I'm going to add and subtract f of x times g of x plus h. So remember that whatever we do to our expression, we have to leave the whole thing unchanged. So what we've done here is added 0. I've added and subtracted the same thing. I haven't changed anything. Okay, so when we do that, let's see. So when we do that, we can go and split what we have into two different limits. So we can split into the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x plus h all divided by h, and then the other two terms that are kicking around we'll put into a second limit. So limit as h goes to 0 of f of x times g of x plus h minus f of x times g of x all divided by h. Now, what we see in the first limit is that in the numerator there's this g of x plus h term that is common to both. It's in both terms. So we'll factor it out of both terms. And we'll get the limit as h goes to 0 of f of x plus h minus f of x. That quantity is multiplied by g of x plus h, and the whole thing is divided by h. Similarly, there's a common f of x term in the numerator of the second limit that we'll factor out. And now what we're going to do is we're going to use our product rule for limits. So we can split up that first limit as a limit as h goes to 0 of f of x plus h minus f of x all divided by h times the limit as h goes to 0 of g of x plus h. This first part is just the limit definition for the derivative of f. So this limit is f prime by definition. The second limit, because we're assuming that g is differentiable, because otherwise none of this makes any sense, so we're assuming g is differentiable, that means g is continuous. And that means we can switch the order of taking the limit and evaluating the function g from one of the theorems we had on continuity. So that is going to allow us to just say h is going to be 0, so we just wind up with g of x. And we can do the same kind of trick for the second limit, and what we wind up all together is f prime times g of x plus f of x times g prime. Okay, so now we want to go and find the derivative of a quotient. Well, we could go and do the same trick as before, or what we could do is cleverly rewrite what we've got and invoke the product rule. So let's say that we have f divided by g, and let's call that function j, whatever it happens to be. But that's the same thing as saying that f is equal to g times j. And if we take the derivative of both sides, then we get that f prime is equal to the derivative of j times g, or j prime times g plus jg prime. And what we said is we want to go and solve for the derivative of f divided by g, or in other words, we want to solve for j prime. That gives us the derivative of f divided by g. So when we go and we solve for j prime, what we wind up with in the end is f prime times g minus f g prime, all divided by g squared. Okay, so let's go and use these in some examples. So first, let's find the tangent line to the function x squared plus 1 times x cubed plus 4 at a equals 1. And we can kind of do this in two ways. So the first thing that we can do is we can write f as a product. It's a function u times v. And we could also expand things out. So we could expand it out as x to the 5 plus x cubed plus 4x squared plus 4. If we write as a product, u prime is 2x, v prime is 3x squared. Using our product rule, we would get that the derivative is 5x to the 4 plus 3x squared plus 8x. And what we could see is if we go back to the original function and expanded it out, if we'd used our sum, difference, constant multiple, and power rules, we would get the exact same derivative. So it gives us two ways of getting to the same answer, which is good. Okay, so we want to evaluate our derivative at 1 and also our function at 1. So evaluating our function at 1, we get 1 plus 1 plus 4 plus 4, which is 10. Doing the same thing with our derivative, we get 16. So from our tangent line equation, we're going to get that the tangent line is going to be y equals 16x minus 6. Okay, so another thing that we could do, so suppose that we're told that the quantity y is equal to u times v. So y is a function, u is a function, v is a function. And we want to find y prime of 2 given information about u of 2, u prime of 2, v of 2, v prime of 2. Well, we know that y prime in general is u prime times v plus uv prime. And if we want to find y prime at 2, that's just evaluating everything else at 2. So we'd get u prime of 2 times v of 2 plus u of 2 times v prime of 2. So we'll just go and put in the givens, and we wind up with a final answer of y prime of 2 equals 1. Okay, for our next illustration, we'll take the function x to the 45 minus x to the minus 45. The first thing that we'll do is our standard stuff. So we'll go and apply our sum difference rules, then constant multiple rules, and then the power rule. But remember that we've said the power rule so far, it only really works, as we've described so far, for positive integers. Minus 45 is clearly not a positive integer. So our derivative of x to the 45 is 45x to the 44. But then we need to come up with the derivative of x to the minus 45. For that, we're going to use the quotient rule. So we'll write x to the minus 45 as 1 over x to the 45, or in other words, u divided by v. So u prime is 0, v prime is 45x to the 44. If we want to find our derivative of 1 over x to the 45, we use our quotient rule. And when we do that, what we see is, hey, it's exactly what we would expect if we just naively applied the power rule. So we would take the power minus 45, multiply it out in front, and subtract 1 from the power. So you would get minus 45, x to the minus 46, which is exactly what we get here. So then using that, we wind up with a final answer of 45 x to the 44 plus 45, because we had a minus minus in there, x to the minus 46. For our next example, we'll take f of x to be 1 over x squared plus 1. So again, we'll go and say that our numerator is u, our denominator is v. The derivative of our numerator is again going to be 0. In this case, the derivative of the denominator is 2x. So we'll again use our quotient rule, so u prime times v minus uv prime all over v squared. And when we apply everything and we simplify a little bit, we get a final answer of minus 2x divided by x squared plus 1, and that quantity in the denominator is all squared. So for our next example, we'll do something, we'll find the derivative of a function that's kind of similar, but now the numerator is 1 minus x squared, and the denominator is still 1 plus x squared. So what we could do is we could do the quotient rule again, as we've just done a couple of times, or we could do is say, hey, we just found the derivative of 1 over 1 plus x squared, so let's make use of that here. So I'm going to write f as the quantity 1 minus x squared times the quantity 1 over 1 plus x squared. So that'll be my u and v, and say we just found v prime. We found that v prime is minus 2x over 1 plus x squared with that denominator quantity all squared, and our numerator derivative is clearly minus 2x. So now f prime of x is just u prime times v plus uv prime, and we'll go and put in what we have for u, v, u prime, v prime, and get, after simplifying a few things, minus 4x all divided by 1 plus x squared with the denominator all squared. Okay, so now what about our new friend e to the x? Well, for the moment, we found the derivative of e to the x is just e to the x. But what about e to the kx for some constant? And that the fact that we're looking at just a number for k is important. If it's some function of x, then we'd wind up with something different. But in the case you're looking at e to some constant times x, that derivative is going to be ke to the kx. And for the moment, we'll just take this as kind of a magic rule. We'll see why this is, I think, tomorrow. So now we can use this to find the derivative of 400 divided by 1 plus 3 e to the minus 0.5t. So as before, we'll go and write this as a u divided by v. In this case, u of t is going to be 400, so u prime is 0 because u is a constant. And for v prime, we'll go and use uh, our sum and then constant multiple rules, and then also this magic rule that we have for e. For e to the kt, where in our case k is going to be minus 0.5. So that'll tell us that the derivative of v is going to be minus 3.5 e to the minus 0.5t. And then putting everything back into our quotient rule, we'll get the derivative of p is 600 e to the minus 0.5t, all divided by 1 plus 3 e to the minus 0.5t all squared in the denominator. The last rules that we want to look at for derivatives are trig functions, so particularly sine and cosine, and then using the relations for sine and cosine, and then also the other rules that we've just developed, primarily the quotient rule. You could find the derivative for tangent or any other trig function you wanted. And then we'll use the derivatives of sine and cosine to come up with some derivatives of other functions. Okay, so to find these, the first thing that we're going to need to do is we're going to need some special limits. So we're going to have that the limit as x goes to 0 of sine of x over x is 1, and then there's a related limit for cosine. So the limit as x goes to 0 of cosine of x minus 1 all over x is 0. I'll show you where the first one comes from, and the second one comes from a very similar argument. So let's say that I've got it set up like this. I've got part of a circle of angle x. I have a point A, B, C, D, and then my origin is labeled O. I have two triangles, so I have the triangle AOB, and then I have the triangle COD that are set up so that the area of the triangle AOB is going to be smaller than the area of the part of the circle AOD, and that's going to be smaller than the triangle COD. All right, so I have something like this. And what we could do is we could find that the area of the triangle AOB is given by sine of x times cosine of x, all divided by 2. The area of the part of the circle AOD is x over 2, where x is that angle. And the area of the bigger triangle COD is sine divided by 2 cosine of x, because it's tangent of x over 2, using our standard base height divided by 2 expression. Okay, so then what we could do is we could go and cancel some stuff off. So the first thing we can do is get rid of all the 2's. And the next thing that I'm going to do is divide each of the 3 parts in this inequality by sine of x. The next thing that we're going to do is we're going to invert everything. And when you invert an inequality, you have to reverse the arrows as well. So if cosine of x is less than or equal to x divided by sine of x, that means sine of x over x is bigger than cosine of x. So another way to see this is 3 is greater than 2, but 1/2 is greater than 1/3. So that's kind of the idea. When you have an inequality and you flip it, you have to reverse the arrows, or you have to reverse the less than and greater than signs. Okay, so that tells us 1 over cosine of x is bigger than or equal to sine of x over x, which is bigger than or equal to cosine of x. And now what we're going to do is we want to take a limit. So let's take the limit of each of the 3 parts in our inequality as x goes to 0. And now what you might be thinking is that this sets up really, really nicely for a squeeze theorem. And that's exactly what we're going to do here. Because the limit of cosine of x as x goes to 0 is 1. The limit of 1 over cosine of x as x goes to 0 is also 1. So from our squeeze theorem, it tells us that the limit as x goes to 0 of sine of x over x is 1. And if we wanted, we could do a similar argument to show that the limit as x goes to 0 of cosine of x minus 1, all divided by x is 0. Okay, so now we'll use that and a standard relation from high school algebra. So one relationship for sines that you might remember is that the sine of a plus b is sine of a times cosine of b plus sine of b times cosine of a. So when we take our limit definition for sine of x, we get the limit as h goes to 0 of sine of x plus h minus sine of x, all divided by h. And then we'll use this relation for sine of x plus h to expand things out a bit. So we get sine of x times cosine of h plus sine of h cosine of x minus sine of x, and it's all divided by an h. So as before, we can split up our limit into 2 different limits that are going to be easier to work with. So one is the limit as h goes to 0 of sine of x times cosine of h minus sine of x, all divided by h, plus the limit as h goes to 0 of sine of h times cosine of x, all over h. In the first limit, there's a sine of x common to both terms, so we'll go and factor that out. And in the second limit, kind of as before, cosine of x is constant with respect to h. As h changes, cosine of x does not change. So using our constant multiple rule for limits, we'll pull the cosine of x out in front, and we'll also do the same thing with the sine of x in the first limit. And now we get is the 2 special limits that we just had. The first special limit, the limit as h goes to 0 of cosine of h minus 1 all over h is 0. The second special limit is 1, and that's just going to leave us in the end with cosine of x. And what we could do very similarly is we could show that that the derivative of cosine is minus sine of x. Okay, so now what we want to do is use these derivatives to just go and just do a couple of examples in conclusion. So the first one, so cosine of x divided by 1 minus sine of x. So at this point, as is typical, we'll go and write things as a u divided by v. Our u is going to be cosine of x. Our v is going to be 1 minus sine of x. So u prime is minus sine. V prime is minus cosine. So using our quotient rule, we'd get something that's kind of big. So we'd wind up with minus sine of x times 1 minus sine of x. And then we're going to subtract off a cosine of x times a minus cosine of x and divide the whole thing by 1 minus sine of x, and that's all squared. That doesn't look great, but conveniently this simplifies kind of nicely. So we can simplify what we've got by expanding it out and get minus sine of x plus sine of x squared plus cosine of x squared. And you might remember from probably high school algebra or something that sine squared plus cosine squared is 1. And that tells us that our numerator is going to reduce down to 1 minus sine of x. And then our denominator is still 1 minus sine of x all squared. So we'll cancel a 1 minus sine of x factor in both numerator and denominator to get a final answer of 1 divided by 1 minus sine of x. If you're wondering about how much simplification you would need to do for homeworks or tests or something, it'll be in the instructions. So if Um, Unless told otherwise, you don't really need to simplify. So for the most part, I'm just interested in seeing that you know how to apply the various product or quotient rules or whatever. I'm not so much interested in the simplification because it's fairly easy to make mistakes there. So unless otherwise stated, you don't need to worry about simplifying things. Okay, for the next example, we have sine of t times cosine of t. So here we'll have a setup for a product rule. U is sine, V is cosine, so U is going to be cosine of t, or sorry, U prime is cosine of t, V prime is minus sine of t. So our derivative is U prime times V plus UV prime, and what we'll wind up with in the end is cosine of t squared minus sine of t squared. And the last two examples are pretty straightforward. So if we have, if we, so we've already said that the derivative of sine is cosine. If we want to find the second derivative of sine, we're finding the derivative of cosine, which we just said is minus sine. So the second derivative of sine is minus sine. So kind of similar to what we said about e. E is its own derivative. The second derivative of sine is minus sine. And then the third derivative of sine is minus cosine. And if you wanted, you could find that the fourth derivative of sine is back to sine. So it nicely cycles. So the standard trig functions cycle for derivatives between sine, cosine, minus cosine, and then back to sine. Okay, so that gives us a good background on the rules for derivatives. There will be a worksheet on this sitting in while courses, so please fill that out and send it to me tomorrow. I will see you in the next video. Bye.